All right. Hello, everybody. Welcome back. The next thing we're going to talk about is logistic growth. Ooh, exciting times. You've seen this before, believe it or not, and it's a pretty cool thing. But the reason we're talking about it is because there's a wonderful differential equation that we can solve to describe what logistic growth looks like. So here's a quick history lesson for you. In 1838, this sweaty gentleman in the background, Pierre Francois Verhulst, believed that the rate of growth for a population, so like a population of animals or humans or whatever, is always going to be proportional to two things. It's going to be proportional to the size of the existing population, and hopefully that makes sense. Populations generally grow exponentially, and so that means that you're growing at a rate proportional to yourself. Bacteria, for instance, we know it doubles every, I don't know, 5 minutes or something, and so it's getting bigger and bigger and bigger proportional to itself. But it's also going to be proportional to the amount of available resources, and this should make sense too, right? If, for instance, humans, we need food to eat, and if there's too many of us, there's not going to be enough food to go around. So our growth rate is proportional not just to how big we are as a species or whatever it is as a species, but also to what is available for you. Mathematically, we would say the following. We would say that, so if P stands for the population, we would know that the rate of change of the population, so dp dt, is going to be proportional. So that's where this r is coming from. This is going to be like the growth rate. Or I guess growth rate. Well, let's always talk about this should be an increasing thing. I was thinking for a moment about, if we had like a half-life, some kind of radioactive decay, that R could be negative, but that's a different kind of problem. Here, R is going to be positive, and that's going to be your growth rate, essentially. So it's proportional, so we multiply by a constant, to P, which is the population size, times the same parentheses, 1 minus P over K. K here stands for, I guess, in some way, like the total amount of resources or something else to that effect. We'll talk about it in class. And so we're basically taking 1, which would be having everything, and we're subtracting off what we're using. So that would be how much stuff is left, right? So 1 is everything. We're subtracting off P divided by K. P being how many people we've got, or what the population is, divided by K, and that being the total amount of resources. Okay, cool. So if we simplify this equation just for now, so that R is equal to 1 and K is also equal to 1, can you all solve this differential equation? The derivative is equal to essentially just P times 1 minus P. How would you solve that equation? So P dt is equal to just P times 1 minus P. How could you solve that? Well, this looks like a pretty good separable equation. So I could divide both sides by P times 1 minus P and multiply both sides by dt to separate my variables, integrate both sides. The left-hand side is going to be pretty challenging. Is there a tool that we just recently learned how to deal with something like this? Yes, partial fractions. Use partial fractions on that side. And then on the right-hand side, the answer is just, the antiderivative of dt is just t. So the right-hand side is going to be easy. For the left-hand side, use partial fractions, and then the right-hand side is going to be t, and then plus some constant. Remember, you have to put an arbitrary constant on one of the two sides. After you use partial fractions, you get something over here. I'll let you all figure that out on your own, and then you can solve for p pretty easily. Cool. All right, that was fun. We'll talk about the answer in class if we need to. But more importantly is I want you to consider the case when R and K are not equal to 1. R and K are variables now. They could be anything. What's the general solution? And I would love it if you would just turn this in tomorrow. Just write this solution out and tell me what the general solution is to this differential equation. Cool. Good luck. Thanks. See you soon.